In this laboratory session, we will see how to verify if a given social choice function is incentive compatible. We will focus on dominant strategy incentive compatibility. During the theory session, you've seen that in order to check if a social choice function is incentive compatible, it is enough to take the Bayesian game induced by the direct economic mechanism associated to the social choice function and check if it has a pure strategy equilibrium where players report their true type. We will study the following example. We have an auctioneer that wants to sell an item to a set of 3 possible potential buyers, and each buyer has a finite space of types where we will assume the evaluation to be in the range going from 1 to 4. The true evaluation of each player on the item are respectively 4, 2, and 1. We want to check whether it is in this setting the first prize auction and the second prize auction are dominant strategy incentive compatible. In order to do so, we employ the following formulation, where the social choice function f depends on the type of the auction we are considering. Using ample, we will check the feasibility of the problem, and if the problem admits a feasible solution, then f is dominant strategy incentive compatible. Now we are going to analyze the meaning of each family of constraints. The first one specifies the utility of each player depending on the outcome. The utility has to be equal to the player's type minus its payment when the player wins the item, and 0 otherwise. Since we have only strictly positive evaluations, the winner can be easily determined by looking at the payment specified by f. Specifically, the winner is the only player with a signed payment greater than 0. To force the utility to be equal to 0 when the player is not the winner, we use the binary variables y. The second family of constraints are such that y of a certain player is equal to 1 if and only if her payment at a given outcome is positive. M is a sufficiently big constant that we can set equal to the higher possible evaluation. The last family of constraints is probably the most important one, since it specifies dominant strategy incentive compatibility. For each player and each possible combination of actions of the others, we are forcing her utility when she plays truthfully, so when she reports her true type, to be at least as good as any other of her possible actions. Now we will see how to write this formulation in ample, and we will start with the mod file. We will see that the mod file will be the same both for the first and second prize auction, and this is because what changes is f, and we encode f, so the social choice function, in the dat file. So the first two sets, P and T, are the set of players and the set of possible types. It is enough to consider one set of possible types because we are assuming that players have the same type space. M is the constant used in the binary variable constraints. TT specifies the true type of each player. And finally, F specifies the payment for each player for each possible combination of the reported types. Now, variable U is the variable telling us the utility for a player at a given outcome. And variable Y's are the binary variables. The objective function in this case is set to 1 since we are just interested in checking the feasibility of the problem. Now let's examine the constraints that we have. The first family of constraints is the one specifying the utility of each player given an outcome. Then we have 2 families of constraint on the binary variable. And finally, we have a group of constraint for each player forcing dominant strategy incentive compatibility. As we said, we have to build 2 different dat files. Notice that the only difference between the two is in the f values. Take, for example, the first submatrix in the left picture. The submatrix specifies the payments of the first player, and this is specified by the last index between the square brackets. The other number that you can find between the square brackets is the action of the third player. The actions of the first and the second player are specified as row and column indices of the 4x4 submatrix. Just to make an example, consider entry 3211. This entry, the value of this entry is equal to 3 because it is the utility of the first player, and this is specified by the last index, and the first player reports type 3, which is higher than the other two, so he wins the item. In the equivalent position of the F for the second prize auction, we find, as we expect, 2, because in this case the highest bidder gets to pay the second highest price. Now let's see what kind of results we get. This is the RAM file for the ample program with the first prize auction dot, and if we run it, the solver tells us that the problem is infeasible. This is in line with what you've seen in the theory lectures, so the first prize auction is not incentive compatible. In the second case, as we expect, the problem turns out to be feasible, since the second prize auction is dominant strategy incentive compatible.